Hello and welcome to another tutorial on dev.java, and we are looking at initializing variables. And we said that primitive variables always get initialized to the default value if they are used as fields or member variables of a class. Fields are member variables. They can be static or non-static. And we said that the default value is all bits are 0. So regardless of what primitive type you use, all the bits of that primitive of that memory location associated with the variable is 0. Byte, short, int, line, these are all zeros in their own respective types. Float, double, again all bits are 0. Char, we said that this is a null character, UTF-16, so each 0 is 1 byte, 2 bytes, it's initialized to 0. And we said that the 0 character or null character is not the same. So as you can see here, I'm defining C5 as a character type with 0 character. So this is not the null character, or sometimes in C language we call this the null termination. In order to specify null termination, you want to escape the 0 with the backslash, which means now they don't interpret it as number 0, interpret it as null character. And we said that if you print a null character to console, it's like it's never there. Null character is nothing, it's not there. And then you can also convert it to UTF. So you say 1 byte and 2 byte. UTF, note that if I specify 3 zeros, which means 1 byte and half, compiler complains, invalid Unicode. A Unicode character in Java has to have 2 bytes, and you represent it with a hex character, right? So you specify that this is Unicode character with these 2 bytes that represent it, right? And I believe if we run this, we had the hex representation of capital Z, for example. So let's and we said that UTF-8 ASCII is compatible with UTF-8, and UTF-8 is compatible with UTF-16. So instead of having a null character in C6, if I use 005A, let's see what happens. And as you can see, we get capital Z. So another way of specifying characters is use the UTF-16 representation. If you're dealing with English alphabet, use ASCII or UTF-8 1 byte representation, right? So 5A is 7 bits active, and then it's compatible with UTF-16. Again, you cannot specify 1 byte, you have to specify 2 bytes, right? So let's go back to the, I typically, for the null character, I typically use this notation, \0. I just escape the 0. And this just says that there is no character. C6 holds no character or null character. Boolean, by default, it initializes to false, right? If you have a Boolean as the field, as a member variable of your class, strings are references, because any object reference is null. And we said that in C++ we have the null macro. So if you include any header file in basically in C actually, right? And C++ or legacy C++, I'm going to write legacy C++ null macro. Whenever you have a pointer type, like some sort of pointer, let's say you have a char pointer A, right? And then you set it to null equal null. This null is actually just 0. All the bits are 0, and we know that a pointer type can never be 0. Basically, when the operating system allocates memory to you, that chunk of memory that is allocated to your application never has the 0 memory address. That's why the 0 memory address is reserved for a null or invalid pointer, a pointer that is not pointing to any valid memory address for your application, right? And we said that in a modern C++, they decided to get away from this macro. The whole macro business is considered a bad practice in modern C++, or basically anything relying on the preprocessor is considered bad practice. So they decided to add a new keyword called null PTR, right? And then it's equivalent. If you have a pointer that you want to see if it's a valid pointer or it's a null pointer, you just assign the PTR to it, or you compare it with a null PTR. But in effect, these two have the same interpretation. Null PTR is now a keyword, so it doesn't rely on macros or being forced to include some header file to get this macro, right? Null PTR assigns 0 to all the bits of this variable, which is a pointer variable type. Now in Java, obviously we don't have pointer types, we have references. So if you have some sort of object, a string s for example, you assign it to the keyword null. In Java they also decided to introduce the null keyword, and null keyword just sets the memory at the value that this s variable holds. This is a pointer in some way, so it's all 0, right? Again, everything is initialized to 0 bits, and the interpretation of the all zeros depends on what type that variable holds. If it's the object reference, all bits 0 means it's a null reference or a null pointer. But we said also that the exception is local variables. Local variables are never initialized automatically. So local variables are slightly different. The compiler never assigns a default value to an uninitialized local variable. So if you declare some variable locally in a method, for example, you have to explicitly initialize it before being able to use it. So if you just declare it without assigning a value and then try to use it, the compiler gives a compilation error. If you cannot initialize your local variable when it is declared, make sure to assign it a value before you attempt to use it. And again, another best practice was to declare your local variables final most of the time, or every local variable should be final by default unless you need to reassign it or change its value. And the other good thing about declaring final is that when you declare a variable as final, you have to basically initialize it. So final variables or even final fields, for example, in a class, they have to be initialized as soon as they're declared. So that's another strong guarantee that the compiler has. When it sees a local variable that is final, the compiler is 100% sure that that local variable has been initialized. Make sure to assign it a value before you attempt to use it. Accessing an uninitialized local variable will result in a compile time error. So it's not a runtime error, so you get a compile time error, which means Java C refuses to compile your source code. Creating values with literals, and we said that what literals are. Literals are anything in your source code that directly maps to some sort of basically a written number, digits or characters or Boolean. These are called literals, right? Anything that comes on the right hand side of the assignment, which the compiler or the Java or the runtime doesn't need to do any calculations on, right? These are just constant variables, and they will be stored as constant numbers or constant characters or constant strings. You may have noticed that the new keyword is not used when initializing a variable of primitive type. Now we know that new is for creating new instances of a class, but primitives are not class, right? Primitives are built-in types. So we don't use new to initialize a built-in primitive type, right? Primitive types are special data types built into the language. They are not objects created from a class, right? Primitives are not objects. Now there is a silent boxing and unboxing that happens. So when we look at the wrapper primitive types, we said that integer is a class, so you can basically initialize a variable of type integer with new integer and let's say 5. Now note that I think from some version of JDK they deprecated the explicit constructors, because they prefer you to use the value of the static factory method, right? They prefer you to use this, and we said that the reason is that there's some caching can happen behind the scenes based off the range of the values, right? But then you might think that, okay, this is a variable x2 and I am assigning a literal, and then so what the compiler does, the compiler replaces this line of code basically with a call to the value of method. And also in reverse, integer x4 is x3, right? What I'm doing is that x3 is an object, but I'm assigning it to a primitive, and this compiles. So this compiles fine. That's because behind the scenes the compiler changes this line of source code into x3 dot int value, a call to a method that returns the int value of this object, integer type, right? So these are happen behind the scenes, and this is called auto unboxing. And these wrapper classes are sometimes called boxed primitives, because these are not primitives based on the built-in types, but these are classes that hold the value or represent the value of a primitive, right? Just be careful about these. Don't use the constructor, or don't explicitly use the new keyword even with the wrapper classes that represent primitives, because those constructors are deprecated, and hopefully at some point they will be removed. Primitive types are special data types built into the language. They are not objects created from a class. A literal is the source code representation of a fixed value. A literal means anything constant, anything fixed, right, in your source code. For example, 100. This is a literal. It's not variable. It doesn't hold the memory address of some Java heap location, etc. This is just constant, 100. Or character C. This is a constant literal. This is a character literal. True is a Boolean literal, which means it doesn't correspond to a variable or anything, right? And if you're familiar with modern C++, these are called R values, and these are something that you cannot assign to them. For example, a variable on the left hand side in C++ is called L value. L value is something that can be representative of a memory address, right? A variable, it's actually holding the memory address of some location of Java heap, but a literal doesn't hold anything, any memory address or anything. It's just constant. So it's a fixed value. Literals are represented directly in your code without requiring computation, right? These are just numbers. They're there. As shown below, it is possible to assign a literal to a variable of a primitive type. Now, we said that obviously if you use final on a local variable, then this kind of also becomes some sort of literal or a fixed or constant value, which means then if you try to use this final variable, local variable, into some computation with other literals, the compiler at compile time can work out the final value or the actual value of that computation. That's why final local variables are kind of like some sort of pseudo literal or pseudo constant. As shown below, it is possible to assign a literal to a variable of a primitive type. So Boolean type, we assign true or false. Characters, we can assign a character literal. Integer types, we can assign integers as long as the number fits. If the number doesn't fit, the compiler refuses to compile. We can force the compilation by typecasting, explicit typecasting, but we also discussed in the previous lectures the dangers of overflow and underflow if we try to force the typecast, right? So integer literals, an integer literal is of type long if it ends with letter L, capital or small l. Otherwise, the default is int, 32-bit or 64-bit. It is recommended that you use uppercase letter L because the lowercase letter L is hard to distinguish from digit 1. So if you have a literal, for example, you want to say long a equals 25. Now this fits fine, but you have to know that 25 on the right hand side is viewed as an int by the compiler, and then there is an explicit implicit promotion or typecasting that happens. If you want to actually tell the compiler that this 25 is actually a long literal, not int literal, you add the postfix L to it, right? And then now the compiler from the very beginning, it sees this as a 25 long literal, right? For int literal, we don't have any postfix or something like that. You just type 25. Values of integer types byte, short, int, line can be created from int literals. By the way, we don't have a literal for byte, short. We don't have basically some letter, for example, capital B or capital S that would represent short or byte. We don't have those. We only have L for long, and int is the default. And the reason is that in modern computation, especially if you're not dealing with the devices that have very strict memory rules, right? Memory is very cheap these days, so normally people just use int and line. There's really no point trying to go through the hardship of using bytes and short There's really no need for that. Memory is abundant in these days, so I guess int and long are enough. That's why they decided to just allow for L, not for capital B or S, etc. Values of type long then exceed the range of int can be created from long literals. Integer literals can be expressed by these number systems. Decimal base 10, digits go from 0 to 9. Hexadecimal base 16, whose digits go from 0 to 9, and then letters A to F. And it doesn't matter if you use capital letters for hex or small letters, both work. Base 2, binary, whose digits consist from 0, 1, right? For general purpose programming, the decimal system is likely to be the only number system you will ever use. However, if you need to use another number system, the following example shows the correct syntax. The prefix 0x indicates a hex integer, and 0b integer indicates binary. Now, Java by default doesn't support octave or base 8. I believe C++ supports that. So let's go back to primitive. I am going to remove these from main method. So let's create a new method, public static void test3, and remove all this code into that. Or actually, let's only remove this code, which is our discussion on the characters. All right, so we create literals for long, for example, with capital L. And then note that if I say int b equals 25, this works fine. If I say 25L, this doesn't work because I'm telling the compiler this is 25L. Even though the compiler knows that 25 as an integer fits in an int, it refuses to compile. It tells you either give me an explicit typecasting, or I'm just going to refuse to compile, right? So you either force it or not. But if the right hand side, which is an integer literal, is larger than the size of the left hand side, then the compiler refuses to compile. And then we said that for integers we have 3 notations. Notation 1 is decimal, right? Integer we mean byte, short, int, long, this kind of stuff, all the 4 types, right? So byte, short, int, and line. When I say integers in this discussion, it means any of these types. But I'm going to use int, for example. We can initialize it with 15 and do a sysout x1. Obviously, this is the normal way of initializing an int. It's very easy in the source code. We just use decimal. But there are also other notations, right? Like binary, right? Int x2. If you want to initialize an integer with a binary, you have to prefix it with 0b. 0b means this is a binary number. And then the digits 15 is 1, 1, 1, 1, right? So this is 4 bits, and base 2, it means 8 plus 4, 12, plus 2, 14, plus 1, 15. So if we sysout x2, note that the print line prints the decimal representation, right? So when you say this, obviously in the Java memory, x2 pointing to a memory that has just bits. But then the way that these methods, for example, print line and the console interpret those variables, it's based on how the integer type is defined for this method, right? So if I run this, I still get 15. I don't get the bits representation. If I want to get the bits representation, I use the integer wrapper class, which has a lot of nice static helper methods or utility methods, and to binary string. It converts to a string, but that string represents the bits. So let's see, let's run this. As you can see, it's 4 bits, 1, 1, 1, 1 as we defined it. And now the third way of initializing an integer is hex, which is sometimes hex is a very nice way of initializing. So 15 is just f, right? 4 bits, which corresponds to f. So I can say 0x, which means I'm defining a hex literal, and f, and do sysout x3. And as you can see, I get 15. I can look at the hex representation, and obviously you already guessed that there is a 2 hex string in the integer class. Integer 2 hex string x3, and it gives me f. Note that a small f or capital F doesn't matter, both are supported. and it still prints F, obviously 15, we're getting that. 2 hex string prints lowercase, right? Now if we want to go to a larger number, this is 1 byte, 8 bits, all are 1, so we can print it is 255. So if we say 255, so 1 2 3 4, so 8 bits, all of them are 1, and 255 all the binary string of x2 is 1. 255 we defined it as hex. And the nice thing about hex is you can use this as bit masks. If you're not familiar with the concept of bit masks, I recommend you to Google it. Sometimes you want to, let's say you have a number, let's say I have these 8 bits, all are 1, right? Let's say I want to only keep the last 4 bits and then remove this, make this 0. So what I do, I define in a hex 8 bits, only the upper 4 bits are 1, and then I can say int x4 is x2 mask it, which means use a bitwise AND with x3 and sys out integer to hex x4. So if you ever wondered what's the use case of bitwise AND, this is not a logical AND, this is bitwise AND. Bitwise AND, which means it takes every bit and AND it with the other bit, and the result is either 0 or 1 for that bit. It's for masking the bits, so F0, right? Because even if these are other numbers, for example 0 0, it doesn't matter, all the lower 4 bits are going to be ANDed with this hex 0, which is 4-bit 0, and they're going to be 0. And then the reason this is useful, then int x5, we can also do a right shift, so we get x4 and right shifted by 4 bits. So this is right shift, this is bitwise shifting, and sys out integer to hex string x5. And actually I want to look at the binary to binary string x5. 1 1 1 1. So let's say now this was 1 0 1 0, 1 0 or 1 0 1 1. Let's say we have an 8-bit number, we want to examine the last 4 bits, right? So you mask it with F0 and then shift it by 4 bit. This gives you just a 4-bit integer, right? And you can examine it. So now we get 1 0 1 1, right? So we mask these zeros and then shifted it by 4. Note that if you can do right shift or left shift, but typically we do masking and only hold the bits that we need, and then right shift or left shift. I believe Java also support unsigned right shift. So if we do this, we still get 1 0 1 1, but Java doesn't support unsigned left shift. Java supports right shift and left shift and unsigned right shift, right? So usually we mask the bits and then we shift to get them. And this is mainly useful, just give you a quick use case, is for RGB colors, right? RGB colors, each one of these, and then we also have alpha or saturate or the transparency. So each one of these is 4 bits, right? So alpha or transparency, red, green, blue, each one of these is 4 bits, which means in decimal the range is from 0 to 255 for red or green or blue, right? So you can see this is 2-byte hex, and this we typically represent this with the integer, right? We can also fit it in a short, so we can say, and then if you have a number like this, a 2-byte, and you want to see what the actual value for the red is, so you mask it. So in order to get the red value, you want to see what integer number from 0 to 255 is. You mask it, you define a mask which is 0x 0, so the 4 bits you want to remove the alpha, and then F, you want to keep the red, and 0 0. So you add the number, the integer you have, or the hex representation of the alpha RGB with this mask, and then after that you right shift how many bytes or how many bits? 8 bits, right? So you right shift 8 bits or 1 byte. So let's say int x6 is or int color. So we have a color in the int space. The transparency is 0, r is 1010, and green is 1100, and blue is 0101, right? And so let's define it as a binary. We defined it as a binary, and then we can int red color is basically we get the color and then bitwise mask it with 0 hex 0 f00, and then right shift it by 8 and sys out red color. So we expect so the first 4 bits are the transparency, the second one is red, right? So let's see. So it gives us 1 0. So let's see this one. So did we make a mistake? So alpha is 1, and then R is 2, and then green, and then blue. Let's say blue is 0 0 0, yeah, or 4. So I think we can also use underscore to better distinguish these. In the any literal, even binary or hex, you can use underscore to better distinguish this. Okay, we cannot do it on the prefix. So transparency 4 bits, red is 4 bits, and then blue is 4 bits, and then green is also, or green is 4 bits, blue is 4 bits. All right, and then we get 6. So red is base 2, 0, and then 2 and 4, so it's 6. So from the range of 255 we get 6. So the most efficient way of dealing with digital colors is to store them in a 2-byte memory address. This is the most compact way. But then if you want to retrieve every individual R or G or B, you have to do a bitwise masking and then shift them. So for red we shift 8 bits, for green we shift 4 bits, and obviously our mask is also different. So I can define let's say green color. So then red is 0 and green is, and then we shift it by 4 bits, right? So green color, and green is 5, right? This is 1, and then 2 is 0, and then 4. 1 and 4 is 5, and obviously blue is 0. We mask it with 000f. So I hope you enjoyed this lecture and now have some understanding of the literals, how we use them, what is the decimal literal, what is the hex literal, and what is the binary literal. I hope you enjoyed this, and I'll see you in the next one.